discussion at the end of the day, one day, and we decided, hey, let's have a conference, and it'll be great. So to see this materialize is kind of amazing. So I'm going to talk about concurrent programming. It's kind of a high-level talk. There's so much in concurrent programming that I'm not going to be able to touch because it's just such a vast subject. This is meant to be kind of just dipping your toes into this vast ocean of concurrent programming. So this is kind of a, I'd say a primer of, what things you should look into that are coming down, things that have already hit from Microsoft, and kind of where we're going. So firstly, for people who may not know me, I just want to clear something up real fast. It's not working.
It's not advancing here.
No. Is the little USB dongle actually in the thing?
Is it?
No, it's not.
No, it's you gotta pull it out.
No, it's right here.
Technology's overrated.
It's tough. It's very
The
single
future is
threaded.
now.
Okay.
Right.
All right. How's that?
Oh,
1 second. Just give it a minute.
I have no patience. I want to go fast.
Yep.
That is the title of this talk.
oh, there you go. Whoa.
Oh, okay. All right. So, just to clear this up, all right? This is not me. Okay? This is very, very clearly Mr. Edward Snowden, all right? Just, this is me, all right? Okay. Clearly very different people. Snowden, let's try again.
3D.
I would go back, yeah.
I'm hitting back.
Oh.
Robbie, are you
There you go.
advancing the thing?
Yes.
You don't trust?
Yeah, got it.
All right, Edward Snowden, Ross Jennings. Different people.
Can you do it one more time? I can't tell the difference.
All right. Ross Jennings. Snowden, Jennings.
All right.
Snowden, Jennings. Okay. Fantastic. All right. So, who am I?
That guy's a dead ringer for you.
I'm an architect here at scusa. I blog here. smugdeveloper.wordpress.com. I only have very few articles, so I'm hoping to increase this number. Obviously, my friends in marketing, they are not here, but they would note the irony in the fact that it's probably a really small font. I don't like WordPress for the enterprise, and I actually shot it down, but I do use it for my personal site. And then my code and the slides for this presentation and all the demos are on my GitHub page. That's static void main. So if you've ever written a console application, static void main, you should be familiar with that. Great. Moving right along. No talk about concurrency is complete without an obligatory reference to Moore's Law. So Moore's Law is something that you have silently benefited from for the last, 40 years probably. And it's not a law, it's just a trend. It was sort of noticed by Gordon Moore, who it's named after. He's the eponym of that. So he's a co-founder of Intel. I'm reading from the slides, which is poor presentation, but I didn't really rehearse this, so we're gonna I'm gonna do that. Come again? Yeah, we'll be fine. So the idea is that the density of transistors that you can fit on a single chip has been exponentially increasing every 2 years. So you're getting faster and faster clock cycles every 2 years. And it was steady for 40 years, and then suddenly it sort of dropped off. And then here's the 18 months, 2 years, right about. More transistors means more. Thank you. So you get more performance for free. It costs you nothing. If you're a software engineer, you're writing software, every 2 years your software just gets faster and faster and faster. You will remember, I assume if you've ever tried to play an old DOS game on a new machine, the clock is insane because they targeted the application to the clock cycles that they had then, and you've gotten so many more clock cycles now that the game is insane. It goes so fast, you can't even make sense of it. And that's in part because of Moore's Law. So this is a chart, shows the steady growth. These are powers of 10. Powers of 10. So, we had 1960, and we're steady. And we kind of hit a bit of a snag around 2003, 2005. Things started to level off for a number of reasons. Some of you may have been in computing this entire time. Maybe not, probably not. But if you're in the mainframe business, you might. None of these names may seem familiar to you.
That's called diminishing. What's that? Return. You just said Marsh.
No, they haven't been diminishing. They've been growing exponentially. Yeah. Power function. We're going up. but we're starting to slow down for a number of reasons. So one of the biggest reasons is something I haven't really looked into. It's something called physics. I don't know too much about it. But it's this idea that we have all this heat and we can't really get rid of it, and then we got to use more power to get, every time we shrink the chips, sometimes we shrink them too small, and then we get this quantum tunneling effect where electrons are actually jumping between barriers and we're getting the wrong answers. So there's a limit to how much we can shrink things down. This is a problem, right? Moore's law states that we're going to get performance because we can shrink things down. We're going to add more transistors, and that's how we're going to scale. So how do we get around this? I guess what's better than one processor with lots of transistors? How about lots of processors with lots of transistors? Moore's law was saved, sort of. So the idea now is that because our single-threaded applications are no longer going to get these exponential performance gains, we're going to have to do a little work on our part, which previously we didn't have to do. We didn't have to care about how we're writing software. We don't care where the OS schedules our tasks. We don't care which thread we're using. For the longest time, it's just been one thread of execution, PowerPC, we're just straight through. But now we got all these threads, we got all these cores, we don't have to do with them. What do do you guys actually explicitly schedule things on threads? Or probably not. You're waiting for the OS to schedule and assign you a little unit of work. I've completely glossed over what a thread is. Hopefully that's acceptable. If you don't know what a thread is, probably not the talk for you. Let's continue. So we can't get exponential speedups in single-threaded code, but if we want peak performance, we can start issuing work on more than one core, and we can get some performance speedups, not comparable to Moore's law scale, but pretty good. We're going to see that you're never going to, you can't add processors and double your performance. That doesn't exist. You're limited to certain things that are not listed on the slide, but if you do a sort of deep dive into concurrency, you'll find that there's like Amdahl's law. Yes.
Are we doing any parallel programming now?
Sometimes. And that's something that I want to kind of break through. That parallel programming is seen as something that's sort of ivory tower. That we know about it. We know that it's probably something we should look into, but I'm afraid of it, or maybe I want to leave it to the domain of experts or something, but I want all of you to sort of at least be inspired to know that this is possible. This is something Microsoft is investing a lot of money into and a lot of research, and it's not impossible. And I want to kind of bridge that. So I know for a fact that there's some asynchronous processing and parallel processing going on in Shane's code for the courier model. There is a bit of, every server, every facade that you're writing is technically concurrent, so you still have to deal with some of these problems like locking primitives and synchronization. Even on your day-to-day facade code, you're running more than one thread of execution. You just don't know it. You're not explicitly scheduling the tasks. IIS is giving you a worker thread to go off and schedule that task. So technically, this talk is unnecessary. You're already doing concurrent programming. Just continue being awesome. Did that more or less, maybe something? Your browsers are multi-threaded. Everybody is doing multi-threading, but you. What are you doing? Use threads. They're fantastic. Actually, as you'll see in a minute, don't use threads anymore. Threads are sort of outmoded, and I'll explain why. So demo 1 is titled Enter the Task. And I will switch over. I'll walk through these slides, and then I'll do the demo. They've done a lot of research. Obviously, they've invested a lot of money. I don't know where I am on time. I didn't even start the timer. I have no idea how fast I'm going, or slowly. This is going terribly. In fact, this is something that I wanted to do because I always see Hanselman do this in his talks, so it's cool, right?
Yeah.
That makes me a cool guy. Now I've lost my presentation.
You've got about 40 minutes, Russ.
Okay, cool. I got a lot of stuff in my demos. I can dive down into sort of my justifications for why I did certain things and different approaches there. So I'll just skip through this really fast. Starting with .NET, we've got this advent of parallel extensions. This stuff, if you follow these really, really bright guys, I don't have them listed in any slide, but if you come talk to me, I will definitely mention Stephen Taub and Joe Duffy. They were kind of critical in bringing easier parallelism to .NET. They wrote these fantastic libraries, one of which is the task parallel library, which all of the new asynchronous features in .NET 4.5 build on, and then plink, which is, I don't know, I kind of feel like link is a bit of a cancer, but it's there. You can add as parallel to any IEnumerable, and it will schedule tasks independently, or it'll try to. You still have to contend with race conditions and stuff, hazards that I'll show you later, but that's available. And then in 4.5, now we've got these crazy async await keywords where we can say, all right, well, I don't really care about the result of this computation right now, so I'm going to schedule it, and then when you complete, call me back with the rest of my code. It's really this tricky compiler reorganization of your code so that you add the await, and then everything beyond, below the await or between the awaits gets scheduled to happen after the awaited thing continues. Anyway, it's hard to describe. It's probably easier to show. I don't really have any examples of await because I don't really want to encourage people to do it without knowing it really well myself. So traditional async programming involved a lot of begin-end stuff where you pass in the continuation for the thing that you're awaiting. There was no await. It was all, do something or begin something, and then inside the begin you would schedule the end callback and say, okay, well, now that it's complete, give me the result of the thing, and then we go off and handle it. So it was a lot of kind of threading the needle through your code to make the asynchronous computation work. You would have to manually set up these callbacks, and it was kind of confusing. So with async, they were trying to make it easier to thread the needle by letting you program in a top-down style, but do that whole continuation passing and threading of state through the continuations for you.
1%. We have to say that these are new thing in .NET 4.5. I don't know whether they are thread safe. Like if you have a piece of code that you want to make sure that only passes.
Oh yeah, that's my second demo is dangerous, and there are lots. You open up a big can of worms the minute you decide to go async. So it's not free, and it's definitely not something that should be taken lightly. You can't just sprinkle await throughout your code and expect it to work flawlessly without doing any modifications. You don't guarantee if something is static. And again, I'll get into race conditions and what they mean and how you can avoid them, how you can mitigate them. But it is by no means completely error-free. And in fact, I might argue that async and await kind of obscure some of the details and make it more difficult. But they are there, and it's important to know about them. And for some things, they are very important and very useful. So anyway, so enter the task is my first demo. Swap over, change the font on Dave's machine so that hopefully you guys can read it. And let me scroll in here. All right, so this is dead simple. The .NET demo is complete without a hello world. It simply schedules a new task and sleeps it just so I don't look stupid. Because sometimes tasks actually complete synchronously, depending on if the task scheduler decides that it's not enough work to really merit actually taking a thread out of assigning it work. Sometimes they will just complete synchronously. So just to make sure that doesn't happen, I've thrown this in here. So if I do this demo, we get a nice console application, and it prints hello from the main thread, hello from another thread. Sweet. So the hello from another thread, even though it came first, if you were going top-down precedence, it came second in the messages that we were seeing. Now, one of the things that this demo is going to gloss over is the fact that console is inherently thread safe. So it's actually locking and preventing any sort of race conditions, which I'll get into later. All right, so that's step one. Pretty boring, not much going on there. I mean, if you want to see the syntax actually of just scheduling a task, it's task.factory, start new, and then there's tons of overloads for this. This one just takes just an action. I don't know if you can see that properly. Does that actually affect the tooltip at all? Maybe. Anyway, so scheduling a task is very, very simple. All right, so that's done there. All right. What else can we do with tasks? We can cancel tasks. All right, so that code looks like this. All right, so some of this may seem a little hokey, but I'll try to go into more detail here. This is a cancellation token source.
Instead of the Windows service that we're using.
Which service, like specific? I mean,
With-
courier services are inherently parallel. They take in requests as they come, and they don't depend on one another, so they're scheduled potentially on lots of different threads, and they don't interact, and so there's no possibility of them clashing ever. Well, hopefully, unless people use like shared variables or something.
So my question is that, is there any preference or which one is better or something like that?
So I'm not doing best practices. I'm just talking about what's available. We generally my feeling about optimization is inspect it, profile it, make sure that you actually have a performance problem before you implement something like this. Because really, the correct solution is really not this. What is it? I've forgotten what I named my thing. Oh no! Crap. I don't have the caching thing on. What's going on? Oh, never mind. Okay. Right. Okay. No, just use cache. Weird. Okay. Oh man. Oh, did I name something else? That just fits. No. Oh man. What have I done? Done the worst thing. Cached. Private line, yes, right, good. Oh, duh. This. There we go. Okay. So really, the correct solution should be this. Oh no. I don't like these laptop keyboards here. Fibonacci numbers, squiggle, go away, squiggle, please go away. This is the universal law of demos. If anything can go wrong, it will.
To his credit, he is using my machine, not his.
Okay, there we go. Sorry, wrong syntax for optional parameters. Okay, so technically, the correct solution is to use caching. So now we can bump this up to a couple hundred, and we'll properly cache the previous Fibonacci numbers and reuse those for every computation that we need it for. Unless I did this wrong, okay, I'm a liar. My demo is bad. All right, never mind. Anyway, but there are other solutions. So parallelism is not always the answer. I use this example because it was pretty easy to do. And it helps simulate some of the latency that you'll see with some applications with respect to long-running things that you want to wait on.
So the question from the previous question, just to follow up, this pattern may not be a good fit for the web request response model.
No, because that's inherently parallel. I mean, that's inherently IIS is scheduling work. So if you're writing a web server or something, unless you have something where you can logically thread things off, and the user doesn't have to wait. The response doesn't depend on the result of a computation. Then yeah, you would not need to do something like this.
I mean, in this case, if we're waiting for a feedback, or one thread is waiting on another one, then event actually should come back and notify. I'm hoping JavaScript or some sort of edX library can help us, because
You're talking about the web. The
yeah,
example is. Yeah.
Mostly our UI is web, right? So that's the way to
Not necessarily.
go.
I'd say more than half the companies writing Windows programs.
This
So-
company. I'm
Okay,
talking about
but
the
yeah,
industry.
in the larger case, yes. The browser can make requests asynchronously without a postback. I mean, this is nothing new. We've been doing AJAX-enabled services for a decade now. So the JavaScript model is single-threaded, but the browser can issue multiple parallel requests. Yes, Marsh.
There's actually a library that's being developed by Intel. I forget the guy's name, but he's pretty big into multi-threading and all that, and he's basically trying to extend that model to the client.
Mm-hmm.
But the library, if you're curious, it's called River Trail. It's actually a pretty cool project to follow, just to kind of see it all in action.
Cool. All right, so now here is bonus round, and you don't get any prize for answering this question correctly, but I will be impressed if you know it. So the question is, what does this print out to the console? What should it print to the console first? And then what does it actually print to the console? And I can zoom that in if you can see. And anybody who has a guess, feel free to chime in at any point.
Docking?
No, it's fast enough that so the sleep is really there just so that it completes. I could put all these tasks in a collection and wait on them if I wanted to, but the idea is I'm going to create 10 new tasks and write the value of I to the console.
Is the answer indeterminate?
So one
It could do a number of
So
different
okay,
things.
so the first one is deterministic. What should this do? I mean,
It should
what did the programmer intend for this?
should go from 0 to 10, but what it could happen is you get a whole bunch of 10s, or 2 5s and a whole bunch of 10s, or any number of things.
He is correct. So why is that?
Because of closures, because that stupid variable I is changed outside of the instance of that function, so you really don't know what it is when it code gets executed.
All right, let's test that theory. Let's see what we got. And I may have given it away with the title of the function, but let's see what function closures actually does. Oh no, we got all 10s. Oh, ay, dos míos. Yes. So he's right. We've created, inside here, we've created 10 instances of a new delegate that captures I, but it doesn't capture it by value, it actually captures it by reference. So what ends up happening is this I, when the compiler rewrites this stuff to deal with lambdas, it actually hoists this up to a local variable bag of closure stuff, and I is a part of it. And so each iteration of the loop is modifying I before the task actually has a chance to go and get scheduled and run. So it actually is indeterminate. Sometimes you get 0, 5, 5, 5, 10. Sometimes you get all 10s. Sometimes you get something close to the right answer, but never exactly the right answer. And you can't reason about it. There's no way, different runs of this could have, wildly different results. Or on my machine, I had different results. I don't know. Dave's machine might be slow. Anyway, so we shall see. Anyway, so you have to be a bit careful when you're doing technically any delegate inside of a loop. Generally, you want to create delegates outside of a loop and then call them inside the loop parameters. This holds true for JavaScript as well. You don't really want to create instances of function objects inside a loop. It's not good for performance. It's not otherwise good. So let's jump back to my presentation. Enter the task. What did I do with the clicker? Here it is. Blah, blah, blah. Okay. So, dangers of concurrent programming. This is a funny joke. This is something I got from Marsh. Some people, when presented with a problem, and this follows a pretty common trope. It's some people, when presented with a problem, I think I'll use this. Now, blank, blank, blank. Something generally to do with how many problems you have. The original was some people, when presented with a problem, think, I know, I'll use expressions. Now they have 2 problems. Some people, when confronted with a problem, think, I know, I'll use Java. Now they have a problem factory. Things like that. So this one is some people, when presented with a problem, think, I know, I'll use threads. Now they have, now too they have problems. So it's out of order because we scheduled them incorrectly. And I clarified the joke in case people don't think it's funny. All right, so one of the biggest and one of the worst problems with concurrent programming is a race condition. So things that are prone to race conditions they can cause your program to crash because you get indeterminate results. Maybe you rely on those results. Maybe the thing that you're expecting has just been nulled out by another thread, and you're like, it's moved my cheese. What's going on? This is terrible. And that's actually the best case. That's the best case because you know that you've got a problem. The worst case is they could mutate shared variables in undefined ways, and you don't know about the problem. and it just silently works for a little while, and then you get some crazy result, and you think, oh, what has gone wrong in my code? And then as a result, report incorrect results. They are very difficult to debug because they're non-deterministic. If you run it on a fast machine, maybe it works all the... Hello?
Hi, this is Zachary with PR, the leaders in home security.
Sorry, I don't have time. Thank you. All right.
Was that set up before?
No, I didn't stage that. That was just some guy.
They call my telephone.
See, things can happen. Non-deterministic things interrupt. So that guy was like the interrupting cow. He was like, I was trying to go on my talk, moo. So if you don't know interrupting cow, that's not smart. So generally, crashing is preferable to silent data corruption because it doesn't always happen that way, but it does. So this was just amazing. I found this on the internet last night, and I had to add it to the slide. This is programmer Ryan Gosling. The meme here is "Hey girl," and then something really geeky that seems romantic because it's Ryan Gosling. So, hey girl, you're like poorly designed parallel code because you generate a race condition in my heart whenever I see you. Aww, poor Ryan Gosling.
Oh, Ross.
You're such a great programmer. That's not me. That is also not me. I wish I was that good looking. I really do. All right. So this is demo 2. Move my cheese. This is going to illustrate, I didn't have fancy animations or anything. This is going to illustrate some basic concurrency primitives that allow you to prevent race conditions. So you're going to see things like mutexes, which are mutually exclusive. So mutex, mutually exclusive primitive that allows a single thread to back up behind one another on top of a shared resource. So that prevents that first problem of race conditions where your variable is getting modified without your knowledge. Reader-writer locks are a more optimized version of a mutex in a sense. They still give exclusive access to writers, but readers won't block each other. So you can have multiple readers reading and not modifying the value, but only a single writer, and then a writer will block all readers. So that's a very specific use case. Semaphore Slim sets the number of flags that can be set, so you have, maybe I only allow 5 concurrent accesses to a variable for some reason, or I want to limit the number of the level of parallelism or the amount of concurrency that's going on. Spin weight is an extremely low level primitive that really just sort of busy waits the processor. It just sits there and does nothing while still keeping the processor hot so that your task doesn't get scheduled off, so that the processor doesn't say, oh, he's doing nothing, so let me give some time to another thread. There's tons more, there's like counting latches and all kinds of random stuff. Again, this is a high-level talk, so there should be probably chapters of books, if not complete books, on all of these things. People invest their entire careers in parallelism, so it's a deep topic that goes very deep. All right, so this is demo 2. How am I on time?
15 minutes.
15 minutes?
No, maybe it's like 10 minutes for questions and 5 minutes.
Okay. Well, I got 2 more demos, so I'll move a bit quickly here.
Go fast.
Yeah, I want to go fast. Okay, so we got data races and we got deadlocks. So here, the first one, data races.
Large text, please.
Large text, sorry, yes, moving on. Set data race. All right, pretty easy to, actually this is kind of fun to set up because one of the problems with multi-threaded code is that it's not deterministic, so making a demo that doesn't make me look like an ass work for some reason because the processor is quicker has been a bit fun and challenging. So here the idea is, I think in setup, do I acquire a lock? No, sneaky. So 5 times, and I'm just repeating this. So this is lots and lots of threads, all trying to increment the same value. Increment value is defined currently as just value plus equals 1. That's pretty safe, right? Even if plus equals is atomic, right? Isn't it? Is plus equals atomic? Yes, no? Show of hands. What do you think?
Yes.
Yes? Dave? It is not atomic. It is a read and then a write. It's 2 operations, and therefore a thread can sneak in between these invocations between the read and the write and produce what is lovingly known in the concurrent problem space as an ABA problem, potentially. So I read one value that is useful if you want to write lock-free code. A lot of the lock-free data structures use the interlocked class internally to do things like compare and swap, to atomically swap nodes, to do a read and write at the same time. And it still allows for full concurrency. These threads aren't backing up. They're simply doing their updates in an atomic way rather than competing with one another and potentially updating the wrong value. Okay, so that's a data race. That is something that happens a lot, or it can happen. And it sucks because you only know about it if you're reporting the errors and if you write good tests and you know that your parallel code is actually doing the right things. The other one is actually a bit more convenient because it actually manifests as your program stopping. This is a deadlock. So getting this actually set up properly was kind of a chore because there's a lot of code here. Can I go into like full screen? Is there even what the keyboard shortcut is? Shift F11 or something? Control Alt F11, Control Alt.
Go to view. Go to view and full screen.
Oh, there it is. For clarification, that is Alt Shift Enter. Sort of distraction-free, more space. So here we have two tasks. The first one is, ignore this. This is just to make the demo actually work properly. But I have two tasks, and they acquire locks in different orders. So this is task 1 acquires lock 2 and then lock 1, and then task 2 acquires lock 1 and lock 2 in that order. So it's obviously this is a contrived example. These locks could be in separate places. They can be in separate classes. They can be in separate files. Everything. So this is just the absolute minimum code I think I would have to write to show you a deadlock. And a deadlock essentially does exactly what it sounds like. So we're gonna end up deadlocking on these two lines. This one here and this one here. Oops, sorry. This one. So because these locks are mutually exclusive and because each thread is taking one lock that the other needs, they both have to halt, and one waits for the other. I read a great thing on Wikipedia that there was a law in Tennessee or Kentucky that no two trains, if they approach each other, two trains must stop and wait, and neither shall move until the other moves. That pretty good? Yeah, I like that. They're backwards.
I don't know, I mean, we have this scenario every day in our database scenario, right? When you write a store procedure
Sure.
and then run in parallel,
Yeah.
and you have not have your operation in the same order,
Absolutely.
the deadlock comes.
Yeah, deadlocks happen. Yeah, so it's important to know what they are and how you prevent them. And one way of doing that is using lock leveling. It's more of a convention. It's really just figuring out in what order your locks are supposed to be acquired and released, and always sticking to that order. It does require some discipline. But generally, when you're writing parallel code, you don't want data dependencies. You want things that are immutable. And apparently Microsoft has just dropped a new set of immutable collections. I didn't have time to actually implement that or include those in my demos, but those are thread safe by design. They are completely unmodifiable after they're created, which kind of seems useless, but when you think about them in the context of threading, because those two things can't share data and can't be modified, you're never in a case where you can accidentally, it's sort of safe by design, which is nice. So I haven't had time to really look into those, but it's pretty promising that those are coming out, and it's indicative of where Microsoft sees the industry going, and that they think that these are the tools that we're going to need in the future.
Ross, I was thinking a while ago about the parallel question. I was referring to as parallel. Can we use as parallel on our collection, any of our collections?
My answer is it depends. As with everything, if it fits your scenario and you know for a fact that, so that's the thing, this requires a lot of discipline. So you get performance speedups, but there's a cost. So you decide whether or not you need that cost, or you're willing to pay that cost, and the maintenance potentially, and so you lose the ability for some junior dev to come in and make a change to that method now that has as parallel. If they don't know what as parallel does and doesn't know what side effects could come out of it, then you've got a bigger problem. So you've saved a few microseconds on your computation, but you've now created potentially hazardous loss-creating bug that is going to be very, very difficult for people to figure out. So yes, by all means, go and use it. No, just kidding. That was sarcasm. But you can use it. Just be careful. Put a comment, warning, here be dragons or something, so people know that there is danger ahead. So this is illustrating task lead all. There are 2 tasks. How am I on time? Am I like desperately running late? Okay, crap. Okay. All right. Deadlocks are boring. Who cares? Not me. Whatever. I'll shift enter again.
For like 3 minutes.
With 15 minutes of questions, or?
Like 3 minutes.
Okay. All right. Here we go then. On and on. I can ramble. So, luckily we're at the last demo. Speed. Okay. Hopefully this doesn't break. I was trying to hit the ball and peak most of the time. If nobody knows what the ball and peak is, that's this. You can read that while I can't do that because anyway. Blood alcohol concentration on the x-axis. Programmer skill on the top there. So this implies that I was drinking when I wrote this code. Hard. There's a Windows ME joke. This is off of XKCD. The slides are available on my GitHub. You can laugh later. All right, great. So this ties into Marsh's example of hubris. So I wanted to demo here for the first time Google Killer v1.0. All right, I'm going to completely take down Google. This isn't a DDoS, by the way. I meant in terms of indexing speed and taking their business. So this is going to index pages starting from a seed. The seed is going to be redundancy.com, just for fun. So we have a variable number of threads that we can add and remove here. And then these counters are going to show us the, and I have no idea if you can actually see these values. I probably should have bumped the font size up or done something clever, but I can't. So anyway, using a single thread and no async web requests, we're at what, 2 pages? I mean, this isn't because I've written inefficient code. It's just, web pages take time to download and scrape the contents and stuff. So not very fast. Not very fast at all. And just so I'm not polluting my backyard here. So what happens if we bump that up and we decide we want to use async web requests? That's kind of cool. We're not actually waiting for the request to finish, but when we do, we call back and we do our processing in the background, so it's sort of asynchronous. Now, Sally, that's much faster, potentially. So we've gotten a lot of speed ups, but there's a lot of code behind this that I'm probably, due to time constraints, I'm not going to be able to show you. So we're sitting somewhere between 15 and 40 pages a second, probably depending on content. It's dipped down to 3.
I think this is impacting the production site.
No, it's fine. Eventually it branches off. I was actually debugging this, and somehow or another we get to all sorts of places. I mean, that's the nature of web crawlers, is that you follow links all the way down. So we have links to Facebook, and I go check Facebook, and Facebook has links to, Yahoo.com, and I go to Yahoo, and you sort of expand out exponentially. I mean, I won't continue this. I'll just stop it right now.
This is one crashed our internet yesterday.
Potentially. Actually, I did this at home. Because I'm not allowed to drink on the job. So that's it. If you want to see the code for that, it's on my GitHub page again. I can show you that information. One last thing, I want to give a very special shout out. Ball and peak, blah, blah, blah. So further reading, Parallel Extensions PFX team on blogs.msd.com. And a special note, thank you very much, Steve Humans, for writing such slow code that I decided to become a performance nerd. All right, thanks guys, appreciate it.
That was amazing. Before anybody steps out, please use your red coupons. And the same thing, we're gonna stand up, move towards the right side of the room for the 3rd door prize. Come on, get the light.